How difficult would it be to reverse engineer a triple element Formula 1 rear wing? Creating a model of a rear wing from images isn't very difficult. Replicating the profile is, mainly because teams have been developing their own since, I'm guessing, at least the 1980s, and probably before then. So unless you have access to a profile, you need some data. Fortunately, there is a paper published for Tyrrell cars from 1989 to 1997. This video will take the data from this paper, then perform a CFD analysis of how the front and rear wings produces downforce within the dimensions derived from the images. The paper I refer to is by Ben Agathoglu and Mike Gascoyne, published in 1998, Aerodynamic Design Considerations of a Formula 1 Race Car. In these 6 fantastical pages gives a breakdown of the important features of a Formula 1 race car from the 1990s. Principles from this paper are still relevant, and I would recommend anyone finding it to read. The particularly valuable part of this paper is the lift and efficiency graphs from the years 1989 to 1997. I'm guessing the lift numbers are from the highest that were achieved for the car over that year. So a lift coefficient of 2.57 for 1990 means a total lift at 45 meters per second is 4,590 newtons. If the rear wing as stated is between 30 and 35% of downforce, it would result in a maximum rear wing lift of negative 1600 newtons. We don't know the ride height. I use the 21mm at the floor's leading edge with 0.2 degrees of rake, like I always do, with the paper stating 1836 newtons produced by the body and floor. The remainder is the front wing with a maximum of negative 1154 newtons. However, this isn't including the positive lift of the wheels, which is substantial. The maximum total downforce I was able to achieve, given the dimensions, was negative 4,130 newtons, and all the difference was from the wings, as I got negative 1,875 newtons for the body and floor, and the majority of this was from the rear wing, because triple element wings are hard. So I'll give an explanation of the front wing first, as this is a little bit more straightforward, as the constraints are a bit easy to grasp. Then I'll present the rear wing, as I was trying to get this right. It took a lot more iterations and effort than I would have thought. The front wing. The standout feature for this car is the raised nose. Its purpose was presented in a previous video, and it was concluded that it was a device for downstream effect. However, it didn't have a well-functioning profile, and had flow separation which I didn't attempt to fix. I fix it here, but it also has a small downstream effect. The issue with the dihedral wing is that the main profile seems to be compromised due to having a very inefficient structure. That is, most of the span is in bending moments. Therefore, it is rather thick compared to other wings of this age. The other problem of this solution for the raised nose concept is the lack of wing surface area. The whole middle part of the wing directly connects to the nose, a long way from the ground, and now will contribute very little downforce. This compares to the Lentonhouse CG901 that had an integrated wing profile under the nose which adds 250 newtons aside from the wings themselves. Tyrrell adopted this integrated design in 1994, before going back to its pioneering concept in 1996. I assume the team lacked the resources to continue the development of the high nose. Related to this problem of the high nose is the discontinuity of the finite wing. The dihedral aspect of the wing mitigates this slightly, but without the ground effects. In effect, there are 2 finite wings rather than 1 at the front. Basically, it doubles the discontinuities and the resultant inefficiencies. Basically, we're talking about a 30% decrease in efficiency per discontinuity. Now some results of 2 wings. A medium and high downforce wing I ran with off-the-shelf NACA 2312 profile for the second element. The medium wing produced 786 newtons of downforce, with 129 newtons of drag at 45 meters per second. The high downforce wing with a gurney flap gave 898 newtons of lift, 165 newtons of drag. The paper suggests that a maximum of 1150 newtons of downforce with an efficiency of around 7 to 9, which would equate to a drag of between 127 and 164 newtons. To try and make things better, I then created a custom second element profile more in line with the images with a larger round on the leading edge. It seemed to match the main element better and added 60 newtons of downforce for 10 newtons of drag. What's actually happening here is the main element has an unusual upper profile due, I suspect, to structural reasons. It is rather thick and tapers to the trailing edge later than is normally the case. Therefore, the angle of attack for the second element may be a bit high. Increasing the radius of the second element's leading edge creates better integration between the elements, particularly with the coefficient of pressure plots taking long span intervals. The dip and spike on the low side of the NACA profiles doesn't exist in the custom profile, means that the turbulence of the NACA profile does not occur with that interaction, such that the slice at 0.7 meters show that the turbulence of the NACA profile otherwise doesn't occur with this interaction. To illustrate a point I mentioned before about finite wings, the main element plot shows that the plot closer to the center line at 0.3 meters is obviously the least effective part of the wing, whereas if the wing was continuous through the center, this difference shouldn't be as noticeable. For the last thing about front wings, I did notice when I added a more effective front wing, the floor's performance drops a little. The plot along the side that is the reason for the increase in performance was reapplied to show that the vortices from the end plate started to re-affect the floor. It seems unless the end plate vortex is not directed outboard, it will drag some of the front wheel wake inboard and under the floor. Now the rear wing. This was way more difficult than I thought it was going to be. The approach I took for this was to run half wings in simulations by themselves, which meant I was able to iterate much quicker. I was able to quickly build the lift numbers peaking with a design that would give me about 1460 newtons, which I thought was close enough to the theoretical 1600 newtons stated by the paper. However, placing that profile on the back of the car made 400 newtons disappear into fat air. Having developed a decent feeling for why this profile worked, I tweaked the profile but could only get back to 1300 newtons. Further tweaking didn't make things better. Considering full car simulations take a day, this is the number that I had to be satisfied with. Now I have some numbers to aim for, and I can make aerodynamic sense of the dimensions derived from the images available. For this car there were 3 distinct setups: low, medium and high downforce. Here I'm trying to replicate the medium and high downforce wings, with an emphasis on the high downforce wing. The size difference relates to the depth of the first element, with the medium being about 150mm and the high being about 230mm, with a gurney flap. I probably would have been lost for longer if I hadn't read John Barnard's biography, where he stated the most important part of a high downforce triple element wing to work is the second element. If the second element is attached, most of the work is done. This rang so true. I thought I was getting close to a result, and the numbers seemed okay, not great, but okay. It seemed that the flow was mostly attached, but then a slight tweak and I would get an additional 200 newtons, and the flow becomes obviously attached, going by the wall shear stress map. The medium wing by itself finished with negative 1172 newtons, 271 newtons of drag. Placing it on the car, this dropped to negative 1034 newtons and 230 newtons of drag. That is removing 12% just because it's behind the driver's head and airbox. But not great, but my aim and emphasis was for the high downforce wing. So I moved on, maybe I could come back to this later. The coefficient of pressure plot suggests room for improvement. The same process was followed for the high downforce wing. Run it in the simulations by itself and add it to the car later. This wing by itself gave 1458 newtons at 422 newtons of drag. I was happy to get within 10% of the stated 1600 newtons from the paper. Then I placed it on the car, and negative 1070 newtons. Luckily, however, it just seemed the second element wing was the problem, and it was clearly separating in the last part of the curve section. Shortening the length of the curve worked. This gave 1298 newtons, which ended up being a drop of 11% from the wing in the free stream simulations. This is also consistent with the medium wing performance drop. As I said, this wasn't satisfying, but whatever I tried, I couldn't improve on this result. The coefficient of pressure plots illustrate the characteristics of these wings. I took one plot along the center line and one 25 centimeters off. Then these can be compared to the free stream simulations. The medium wing shows a consistent characteristic, though it has less area than the free stream simulation. Differences between the center line and the off-center plot illustrates the influence of the car's body. Again, similarly with the high downforce wing. However, this is comparing the free stream prototype with the final test wing that was tweaked. This difference isn't as dramatic as comparing the medium and the reflected percentage loss at 11 versus 12. This basically finishes my attempt to reverse engineer this car's aero, as downforce is what characterizes these cars the most. The Gascoyne paper mentions the efficiency, so we might as well derive and compare the drag results. The efficiency was stated to be 2.86, where I got 3.19. It seems like this is mostly the wheels, as the paper states that there should be about 40% of the drag. I'm getting about 20%. So these simplified wheels are rotating, but obviously not generating nearly as much turbulence than they would otherwise. But then there isn't brake ducts and brakes and etc. Though saying this, another model I simulated, the March 88-1, had wheels contributing more than 40% of the drag, and these are the same wheels. But then the 88-1 was a much more efficient car generally. In the real world, it produced an efficiency above 3 anyway. Lastly, the downforce distribution the paper was using is 36%, which is basically the same. I was getting 3,118 Newton meters about the rear wheels, with the wheelbase being 2.92 meters.